Good morning, everyone. We'll be starting shortly, so please take a moment to make sure that your microphone is muted to avoid any interruption during the sessions. Thank you for your cooperation. Good morning, everyone, and welcome to the day 2 of the third virtual course 2024. And this event is hosted by Faculty of Pharmacy, Universitas Indonesia. And please allow me to introduce myself. My name is Donna Mareta Ariestanti, and I will be your moderator for today's sessions. And a little bit of introduction about myself. I'm a faculty member of Faculty of Pharmacy, Universitas Indonesia, and I completed my undergrads and also professional pharmacist training at also Universitas of Indonesia, and later pursued my master and doctoral degrees at the Tokyo Institute of Technology in Japan and finished my PhD course in 2015. My research focuses on natural products, molecular pharmacology, and also drug discovery, focusing on the explorations of natural products. And before we started, just a quick reminder that the link for the attendance form and evaluation survey are available in the chat box. And please make sure to fill them out for your certificate of participations. And now let's turn to the highlight of today's sessions. It's my pleasure to introduce Dr. Ut Dong Tat from Ton Duc Thang University, Ho Chi Minh City, Vietnam. Dr. Tat, are you here with us now?
Yeah, I can hear you.
Okay. Okay, welcome, and how are you, doctor?
Yeah, I'm very good, thank you. Good morning, everyone.
Yeah, it's so great to have you with us today, and we've been looking forward to hearing your insights and also learning more about your work. So before we begin, please allow me to share a brief overview of Dr. Tat's impressive profile. So Dr. Ut Dong Tat is a lecturer in the Department of Chemistry at the Faculty of Pharmacy, Ton Duc Thang University, Vietnam. He earned his PhD in chemistry and physical chemistry of materials from University of Montpellier, France, where his work focused on functional materials and nanoscience. And Dr. Tat's research interests include the isolations of semi-synthesis of natural products and also the development of biodegradable drug discovery systems and also the synthesis of hydrogels for biomedical applications. His innovative projects range from creating selective absorbance materials for pharmaceutical use to advancing methods for evaluating natural product bioactivity. As an accomplished scholar, Dr. Tat has published extensively in international journals, contributing significantly to natural product chemistry and also material science. We are fortunate today to have him share his knowledge with us today. And let's welcome Dr. Ut Dong Tat, who will be presenting his lecture with the title Isolations and Semi-Synthesis of Natural Compounds. Dr. Tat, the time is yours.
Okay. Yeah, I'm sharing my slide. Okay. So, are you seeing my slide? It's okay?
Yes.
Yes, we can see.
We can see
The voice is also okay? You can hear us? You hear me also?
Yes.
Yes.
Yes, we can hear you loud and clear.
Okay. Thank you. So I will start now my talk today. So first of all, I would like to thank the organizing committee, the Faculty of Pharmacy, University of Indonesia, for inviting me to give the lecture about our work recently. And I would like to thank the Dr. Donna, for your kind introduction about me and my work. So for today talk, I would like to discuss about the isolation and semi-synthesis of natural compound. So this is my name, Úc Dòng Thật, and once again, I am a lecturer at the Faculty of Pharmacy, Tôn Đức Thắng University, Ho Chi Minh City. So it's Ho Chi Minh City is one of the biggest city in the south of Vietnam. So in area of Delta Mekong. So would like to see you in the future in our university. And also I saw some video from your faculty, your university also, and I see that your faculty and university have a very beautiful campus and very modern facility for research. So I hope that in the future we can collaborate for the research and also education. And so before I begin my talk, you could also stop me anytime if you want to ask something, or even at the end of my presentation, you can also ask the question. So it's okay for for the beginning. Hello. Yeah, do you hear me? Okay. And for
Yeah.
student also, you can also ask me the question if you want, yeah, when I start my presentation. So once again, I would like to introduce myself. So she already introduced, so just a little bit. I got my PhD degree in chemistry and physical chemistry of material at the University of Montpellier, France. And now I work as a lecturer at the Faculty of Pharmacy, Tôn Đức Thắng University. And yeah, my research interest now is organic synthesis and biomaterial. That's the two area that I will focus now for my research. And okay, I will start with the talk today. So you know already, maybe in your faculty also there are some specialists of professor who already taught you about the natural compound, natural products, and this very familiar in the world today for the research about the natural compounds. And this is, I just show you the diversity of sources that we can isolate the natural compounds. So which one do you already use? You can also send the information to the chat box also, you can share with us the source or the sample that you already know or you already study about the natural compound, natural products. Okay. Anyone? What do you know about the natural compound or natural products? You could also share with me also. Dr. Donna, what kinds of sample do you work now?
So I mostly used plants.
Plants, yeah, higher
Yes,
plants. Yeah.
that's my research.
Most
Yes.
most of researchers now focus on higher plants and medicinal or herbal medicinal and herbal plants. So because it's very easy to collect the sample. It's popular. Yeah. Another student.
Yes, sir. Also, as in Uganda, we mostly use plants.
Yeah, must use plants. So why we choose plant for study about the natural compound? Mostly, okay. Yeah. In our country also, normally we focus on plant, medicinal plant that we use in traditional medicine also, because that's sometimes it's already used on the for human, and it's kind of safe for study and use of this compound. But in general, for the natural source, we can also think about other sources. For example, lichen is also an interesting source for the study of natural compound. And this is the combination between the fungi and bacteria. And this will also give interesting biological active compound we can isolate from them. And another example, we can also isolate the natural compound from fungi. And an excellent example that I believe that you already know, the penicillin antibiotic, and that's isolate from fungi Penicillium species. And other sources, we can also isolate the bioactive compound from bacteria, from insect, from animal. And nowadays, there are good attention about the marine natural product. So we could isolate the very strong biological active compound from marine species. And so for the natural compound, we have another term that we call secondary metabolites. So we have secondary, so we have also the primary metabolites. So do you know about the primary metabolites? Before we start with the secondary metabolites, what kinds of compound that we call that primary metabolite for student? So it's online course, so you need to interact with me, that I feel I'm not lonely and talking with my computer. Yeah. So normally primary metabolite is the compound is vital for the growth and the life of organisms. We have ADN, we have protein, we have lipid, carbohydrate, etc.
Hello.
And yes,
Yeah, our primary metabolites they are compounds which are
yeah,
produced by plants or other organisms that
yeah,
are directly involved in
yeah,
growth, development, and other physiological functions.
yeah. Okay. So give me some example that you know about the primary metabolite example.
Some of the examples about some of the example of primary metabolites we have carbohydrates,
Yeah, carbohydrate.
we have proteins or
Yeah,
amino acids.
yeah,
There are
okay.
lipids,
Yeah,
nucleic acids,
yeah,
and
very,
other organic
yeah.
acid.
Yeah, okay. Amino acids. Yeah. Okay, very good. Yeah. And for the natural compound, we focus on the secondary metabolites. Normally, that's not essential. Yeah, it's not vital for the growth and life organism, but it's essential for the interaction between organisms with the environment and the produce is produced is in the response of stress. So that's why normally the secondary metabolite will have the biological activity, because that's why the nature produce the compound to protect themselves against the stress environment. And so that's why we focus on the secondary metabolite. And normally the first purpose of secondary metabolites that we view as the medical, yeah, for the treatment. And nowadays we also use for the domestic and other demands of our yeah. So this you can also think now, yeah, there are a diversity of sources that we can focus on, yeah, to study the biological compound. And when we change the source, we also have the new technique to identify or isolate the compound, because the chemistry is not the same compared to one source or another source. For example, from marine natural product, normally we will obtain a very complicated chemical, yeah, compound, but not they will have the strong biological activity. So you can also think about marine natural product, especially like Vietnam and Indonesia. We have a very long sea, so we can also collect the marine marine species to study, yeah, the biological compound. So this is the introduction about the source of natural compound that we can also think about that. And this is the step for the study of natural product. So yeah, if you already work in the field, you can also feel familiar with the technique. So the first step that we use we must to collection the sample. So this first step is very important, and the most important thing that we need to identify the scientific name. So you normally we will you ask for the specialist to identify the sample. Nowadays we can also use DNA identification for exactly identify the scientific name of the sample. And for the next step, we use the extraction technique to extract the biological active compound from the natural source. And I show you here two traditional extraction technique that we normally use in our lab also. We use Socklet extraction and hydrodistillation. So hydrodistillation, what kinds of sample do you know the hydrodistillation and what kinds of application we can use for the extraction of natural compound? About Socklet also, do you know about Socklet extraction? I brought here different kinds of extraction technique also. Yeah, just introduce with you. Maybe you will familiar with one of the extraction technique. Hello.
Yes.
Okay. Do you know hydrodistillation? What's the application for this extraction technique?
Can I answer?
Yeah.
I think everyone's still shy.
Okay.
Tony, are you here, Tony? You usually quite active.
Yes,
There's one.
yes,
student.
I'm
Yes,
here.
it's for essential
Okay,
oils, right? You want?
Yeah, essential oil.
Yes.
Okay, thank you. Yeah, there are different kinds of extraction that we can use. So for if you want to use the essential oil, you use hydrodistillation for the extraction. And other technique we will use for the study of natural compound normally. And when you want to choose the technique of extraction, you can it depends on the purpose of the research. For example, if your sample is very expensive and you want to extract total of the compound in the sample, you can use Socklet extraction. Yeah, you can use for many time extraction, and we can economy the solvent also. And if you have a lot of sample, you can use maceration extraction with methanol, ethanol. Yeah, you can get the total extraction. And after that, we can use liquid extraction to fractionate the total extraction into different fraction. And it depends on the polarity of the compound. So the second step is extraction, and the third is the isolation. So here I have three techniques of isolation. We have column chromatography, gel filtration chromatography, and ion exchange chromatography. So the mechanism of isolation is depend also different techniques. So for the column chromatography, we separate the compound depends on the polarity of the compound. So we use a normal phase or reverse phase. It's dependent on the polarity of the compound. If it's low, moderate polarity, we can use normal phase. But for the compound with high polarity, we must use the reverse phase chromatography. So the first technique that we use that we focus on the physical activity property of the compound. That's the polarity. And in some cases, we have a very complicated mixture of the compound, and they have very similar polarity, and we cannot isolate with the column chromatography. So we must change the technique into gel filtration. And the gel filtration is based on the volume or the size of the molecule. So we use another property of the compound to separate those compounds. And some natural compound will have the ionic group, so we could also use the ion exchange chromatography for separation. So it depends on the compound, on the polarity, on the volume, on the charge of the compound. We choose the technique for isolation. So it gives you a general idea and about the isolation. And after isolation, it's the more complicated part, and it also needs a lot of time to learn and practice to be good at the chemical structure elucidation. And normally we use spectroscopy technique. We use FTIR, UV-Vis, HRMS, and NMR for the structure isolation. I will give you a sample exam later about the one compound we isolate in our group. Yeah. And this is the step for the isolation of natural compound from sample collection, extraction, isolation, and chemical structure elucidation. And so from now, if you have any question or would you like to discuss with me something about the isolation? Yeah, you can also ask me before I will next to the next step. Okay. Do you familiar with those techniques? I believe that this is very familiar in the world, and normally in the Faculty of Pharmacy, there are a group of phytochemistry who work about the natural compound isolation, extraction, and identification of the chemical structure of the compound. So,
Excuse me.
yes.
Thank you very much for the explanation on the isolation of natural products. According to my knowledge, we know we start by the collection of plant sample or any sources of our drugs. Then we
Yes.
go to extraction. I wanted to ask, are they like before going to isolation, there are always some screening processes that we do. Do I consider it to be under extraction? Like using the high throughput screening or the low throughput screening?
What do you mean screening about the biological activity, right?
Yes.
Okay. Yes, also in the normally in medicinal, there are also the step that you could also apply, that you will test the biological activity first, and we could identify which fraction will have the highest biological activity that we can follow. We call bioguide for the extraction of bioactive compound. Yeah. You can also ask this step in your process, and this will be give you the information, and maybe you will find the good bioactive compound later. But normally when we study the extraction and the pure compound, and this is different. Normally it depends on the sample also, but normally the extraction will have more the biological activity than the pure compound, because they have another compound in the mixture, and that could have improved the biological activity. And normally when we find the one extract the fraction that have the highest biological activity, and when we isolate the compound, this pure compound don't have the good the good biological activity. So yeah, you can also study first about the biological activity for the fraction, and that could help you to identify which part of the fraction you can continue to do your research. For me, I focus on the isolation of pure compound, and after that, I study about the biological activity later. And if the compound have the biological activity, I continue to modify to do the semi-synthesize to improve their biological activity. So it depends also on the approach of the group. Yeah. So is it clear for you? Do you have other question?
No.
Yeah. Okay. Thank you. Yes. Yeah. It's very good question about the step. Yeah. Okay. So it's either the second step. Yeah. That's I already. So normally we find the natural source to isolate the natural product, and we test the biological activity. After that, we can also improve the activity by semi-synthesis. So this is a general step for the drug discovery to find a new compound which have the biological activity for the test later. So yes, this is the general introduction about the isolation and semi-synthesizer. And nowadays, some the drug the approved by FDA normally come from around 20% of drug come from the semi-synthesis. So that's a good indicated that the semi-synthesis compound could be used as a drug for the drug discovery. Okay. And for our study, so it's in our work in our group now. So I would like to introduce some our recent work about the xanthone. So this is the chemical structure of xanthone. They consist of two aromatic ring conjugated by the carbonyl group and one atom of oxygen atom. And it's a planar structure of xanthone. And from the aromatic ring, we can also have different of functional group could be changed to obtain the a big or family of xanthone compounds. And until now, we have researchers already found around 700 xanthone compound in nature, and that could isolate from higher plant fungi and lichen. And why we focus on xanthone? Because this compound have a very interesting biological activity called, for example, antibacterial, antioxidant, etc. And this is some example of xanthone compound that we xanthone plant, xanthone rich plant that we could isolate, that is also very popular in Vietnam, and we can collect the sample very easily. I believe that some of plant can also found in your country also. Yeah. And in our group now, we focus on the Garcinia genus. So it belongs to also a very famous fruit, mangosteen. Yeah, do you know this kind of fruit? Yeah, this popular also in your country. No? Yeah. Normally I saw that
Yes,
also
I
in Thailand.
know.
Yeah, no?
Yes,
No.
yes, I know that one.
Yeah,
It
okay.
is in our country.
Yeah, okay, thank you. And other also genus of the Garcinia, yeah. We focus on this specific genus because that contain a lot of xanthone, the compound that we focus on the study in our group now. And so this is the example of isolation, extraction and isolation of alpha-mangosteen. This compound is very famous and they already isolate for a long time ago. But now it's gained a lot of attention of the bond activity that I will show you later. So for the isolation, it's very easy for the natural, for the phytochemist. So we focus on the peel of the mangosteen fruit, and we obtain the raw material. We use chocolate extraction with the dichloromethan. So we also already optimize the extraction process because this compound, when we use the dichloromethan, this compound, we can extract the compound with the purity around 60-65%. And after that, we should simply use one column chromatography, and we can obtain the pure alpha-mangosteen compound very easily with a very high quantity also, and it's enough for our semi-synthesis later. And so if you work in the phytochemistry group or natural product, the first, when you isolate the compound, you must to test about the purity. So TLC, thin layer chromatography test is very convenient, non-expensive for the test. And this is one example that I show you. It's my student. They test about the purity of the compound. Normally, we must to choose different nature of the mobile phase with different solvent, and then to test about the purity, and the place of the post must to be different, like in the picture here. And normally when we saw that there are only spots here for the compound, and we can conclude that our compound is now pure, and it could be sent for other for the spectrometric characterization. So this is the first step that we make sure about the purity of the compound. If we see different spot when we change the polarity of the solvent, the nature of the solvent, we must to reduce the isolation to obtain the pure compound. So, and after that, we test about the quantitative, about the purity by SPLC, and this is the SPLC chromatogram that we obtain from the alpha-mangosteen. And the principle is very simple. We use the peak integral of the main peak, and we divide up the total peak with the other impurity here, and we can also calculate easily the purity of the compound. Is very high purity, suitable enough for biological tests and also for the semi-synthesis. So you see the purity test. You can use thin layer chromatography for the first step. It's convenient. It's not expensive. And after we sure that our compound is pure, we can move to the SPLC for the quantitative test of the purity. And after that, this is the result of the FTIR spectrum of the compound. So from the FTIR spectrum, we can identify the functional group of the compound, the bond. Different kinds of the bond will be identified from this technique. So you can see here, this is the typical signal of the OH. This is the typical signal of CH, saturated CH. We have also unsaturated CH bond, but it cannot visit here because the OH peak is very big. We also identify other bond like CO-CC double bond or CO single bond here. So that will give us the information about different kinds of bond. And this is the UV spectrum, and we identify two peak of the in this spectrum that belong to the conjugate bond, double bond of the compound. And after that, this is the proton. You need some time to learn and practice about the proton. And I also just show you the requirement of the pure compound. If you wrote in your thesis or your paper that I can isolate this compound, you must to prove that by the spectroscopy methods. And normally they will require you FTIR, proton, and carbon, and also other technique if the compound is complicated. So this is the non-compound. So we just only need the proton and the carbon to confirm the chemical structure of the compound. This is the carbon spectrum of the compound. And another technique, normally the journal, when you plot in your thesis, they also require for the mass spectroscopy. So this will confirm about the molecular weight of the compound. And normally we use the high resolution with the 4 shift after this font to confirm the structure. So yeah, this is just give you some idea about the different kind of spectroscopy to confirm that we have the pure compound and confirm the chemical structure of the compound before we go into the biological test or doing some kinds of semi-synthesis later. And in our group now we focus on synthesize on isolate some of xanthan compound, and this is some of the example that I will discuss later about the biological activity. So I just show you the chemical structure and the name of the compounds and I will discuss about the biological activity later. And so this is the isolation. And in our group now, we focus on the chemical modification. So we first start with the alpha mangosteen, so we can isolate with the high purity and a lot quantity for semi-synthesize. So the very easy reaction that we can use, that we can isolation of the phenol group here. That's very well known. There are lots of reaction that you can find in the internet, and you can do the isolation. And after that, we also think about the reaction about with the alkane group here. So we try to cut this group to form the dialdehyde group, and this could be used as the intermediate for the synthesis of other compound. However, this reaction now is we need to optimize because the yield is not very high now. So we must to optimize, and after that we can synthesize higher compound, high quantity compound, and could be used for other chemical modification. We could also modify the alpha mangosteen with epine chlorhydrin. That's compound you can see here. And we can obtain the deepoxide mangosteen compound, and this very active compound that we can use for the modification later. This is also an intermediate, and we can also react with the amine compound to obtain the diamine, beta amino derivative. And also we also synthesis other compound that we could improve the solubility or the biological activity of alpha mangosteen. We can also synthesize the diacid compound. So normally mangosteen is have very low solubility in water. If we change into diacid compound, so this acid group could be improve the solubility of the compound, and we hope that we can improve the biological activity of the compound later. And another step, another semi-synthesis approach that we can also synthesize the diamino mangosteen. And some research show that the diamino mangosteen will have a very strong biological antibacterial activity because of the positive charge of the amine group could be benefits for the antibacterial activity. So this is some of example that we could use the chemical modification to synthesize different kinds of derivative of the alpha mangosteen compound. Yeah, this is the semi-synthesis step. And on of this step, we already we perform this in our group now. And just here, I would like to share about the activity of the compound. So we isolate, perform some kinds of chemical modification, and after that we must to prove about the biological activity of the compound. And this research was performed under the collaboration with Dr. To Tham Thi from Hanoi University, she in the north of Vietnam. And she focused on the evaluation of the biological active compound. And normally we use the Megada fish model. Normally we use shell or we use mice model, but in our group we focus on the fish model because it's convenient, it's non-expensive, and like we can get the result very quickly to screening the biological activity of the compound. And this is another step of the study of natural compound. So the first one we must to study about the toxicity of the compound, and we design this experimental based on the OECD guidelines for the testing of toxicity of the chemical. So in general, we collect the embryo or the larva, we expose with our compound, and we observe the survival or the malformation during the time, and we calculate the results after. So this is some of the result that we obtain now about the toxicity of the xanthan compound with the embryo. So because the embryo have the membrane to can protect the fish, so normally our compound to have any toxicity, don't have any toxicity about this model. However, when we change to the larva, we can observe that the compound will have the toxicity. It depends on the chemical structure. They are xanthan compound, but they have the functionality. They will have the different biological activity. And we identified that there are two of our xanthan compound have a very strong toxicity. That's alpha-mangosteen and covanol. The structure I already showed you, the chemical structure of this compound. And we estimate, calculate the survival rate and also mortality rate. And this is the summarize of the compound, of the toxicity of the compound. So that I already tell you about the alpha-mangosteen and covanol. These two compounds have a high toxicity to the Mecada larva. However, the semi-synthetic compound is the acetylation compound that you can see here. They have a very low toxicity. So that is the evidence that we can, when we semi-synthesize, we can modify the compound, we can reduce the toxicity of the compound. And this also familiar when we observe with other compound. I know that's one excellent compound that we synthesize aspirin from salicylic acid. So when we change from salicylic acid to aspirin, also by the acetylation, and we can create a very interesting compound for the use as the drug now. So we also learn from that, and we would like to study, and we also luckily to reduce. Yeah, we could reduce the toxicity of alpha-mangosteen, and the bond activity later is also very interesting. After the study of toxicity, we evaluate the bond activity, and we use the transgenic Mecada fish model. In general, we create the disease for the fish, and this is the rank plus is the fish which have the gene for the osteoporosis disease, and the rank negative is the normal fish. Don't have the gene for the disease. And also we can observe the transgenic process by labeling the gene, and we can observe the fluorescence of the fish. Yeah, this already developed in our group long time in 2012, and we can use this model for evaluate our compound. And this is the procedure. We collect the embryo, and we after 7 days we trace our the fish with the compound, and we use the heat shock to activate the disease, the osteoporosis disease, and we observe the fish after 1 day, after several days. Yeah, and you data analyzing. And this is the protocol for the analysis of the bond activity. Normally, we use IMAJ to measure the length of the bond. Yeah, and we cumulate the length of the bond, and we calculate that we call the index bond of mineralization. Also, we can also calculate the index of bond protection by comparing with the control group. Yeah. And these two of the index will give us the information about the bond protective activity of the compound. And I just show you here the bond activity of alpha-mangosteen compound in the index of mineralization and index of bond protection. If we compare with the negative control and also positive control, the alpha-mangosteen will have the bond activity and show the potential. However, when we increase the concentration, the dose, we observe that there are the reduce of bond protective activity. So that's explained because the alpha-mangosteen have a toxicity. When we increase the dose, it's have a harmful effect on the fish. So that's why we observe that they reduce of the toxicity. This is the toxicity or the bond activity of other compound that we isolate and evaluate in our group. And normally xanthone have the bond activity. It depends on the structure of the compound. And so finally, this is the very interesting works that we do now, because when we obtain we synthesize the diacetoxy-mangosteen compound from the native alpha-mangosteen compound, and we can reduce the toxicity. The alpha-mangosteen compound is very toxic. We can use in a very high dose. However, when we reduce the toxicity, we can also increase the dose of the compound, and we can obtain the bond protection index up to around 60%, normally 2 times higher than the native alpha-mangosteen compound. And that's just an example. Give you another example for the isolation and semi-synthesized could improve reduce the toxicity, and in the same time we can also improve the biological activity of the compound. Yeah. So this is all of I would like to share with you today about the isolation semi-synthesized, and very simple example about the isolation and semi-synthesized of alpha-mangosteen. You can find that in the internet, the semi-synthesized, they have a lot of publication about the semi-synthesized of alpha-mangosteen. However, our group now focus on the bond activity of those compounds, and this is the first group, I believe, who have the study about the bond activity of alpha-mangosteen and their semi-synthesized derivative compound. And okay, this is the end of my talk today. Thank you for your listening, your attending, your time also. So if you have any question or would like to discuss with me, so please.
Okay, thank you very much, Dr. Uttongthap. So now it's time for the Q&A sessions. If you have any questions, please use the raise hand feature to ask directly, or you can type your question in the chat box. If you like to ask in Bahasa Indonesia, feel free. I will help you to translate it in English. Okay, so is there any questions from anyone? It's very interesting. Thank you for the insightful and thorough explanations about your work. So I have some questions actually, but let's give the chance for the audience first.
Okay, thank you.
Anyone who wants to ask?
Hello.
Yeah. Okay, Tony, yes.
Thank you so much, Professor, for your wonderful presentation. So I followed your explanation on the thin layer chromatography. Now the TLC.
Yeah.
I wanted to inquire, like, what is the indication of the RF value, like in that case, and what are some of the limitations of using the TLC in the in the identifying the purity of the sample.
Yeah. Okay. Yeah, we normally use also RF also for the thin layer chromatography. But in my example, I just show you about the principle to identify the purity of the compound, and the limitation that we normally when we saw only one spot on the thin layer TLC, we don't know exactly about the percent, the quantitative percent of the purity of the compound. And also in many cases there are also other impurity that we can observe on the thin layer chromatography. So we need use another technique like SPLC to confirm the purity. But normally I will ask my student to test the thin layer chromatography first, because this is very convenient, non-expensive, and we can conclude about the purity before to send the sample for the spectroscopic analysis or SPLC analysis, because it's expensive. So that's why we must use thin layer chromatography, and normally we use that every day in our group. Yeah, for the semi-synthesis also to observe the semi-synthesis reaction, yeah, to verify the purity of the compound. Okay.
Okay, any more questions? So maybe I will start
Hello.
one. Oh, okay, Tony, you still want to ask questions? Yes.
Sorry.
Oh, okay. I'm sorry for over asking the questions.
Yeah.
I would like to know the difference between xanthones and these other classes of the phenolics compound, like the flavonoids or the
Yeah.
alkaloids. Like,
Yeah.
what differentiate them from those?
Yeah. Xanthone is also belong to the phenolic compound, because they contain the OH group with the phenyl bond to the phenyl group. So some of xanthone, it could be classed into belong to of the phenolic compound, and phenolic flavon or alkaloic compound is another family. Yeah, alkaloic normally they will have the nitrogen atom in their structure, and flavone they have another compound, they have another structure. Yeah. So, and for the xanthone, they have the planar structure with two aromatic ring, and they can connect together two aromatic ring with the carbonyl group and oxygen group. So if we have this structure, we can call that is xanthone. And there are lots of xanthone that we can also change the functionality of from the aromatic group, and we can obtain a lot of we could also build a library of xanthone, yeah, compound based on the basic structure. You still see my slide also?
Yes,
Yeah.
we still can
Yes,
see.
I can see.
Yeah. This is the introduction about the xanthone here. Yeah. The xanthone will have this noyl group here. We have two aromatic ring, A and B, and connect together with the carbonyl and oxygen group. And if they have the OH group on the aromatic ring, this could belong to the phenolic compound. Yeah. Okay. Other question, Tony?
Excuse me, I would like to ask a question.
Okay.
Yes.
Yes.
Firstly, okay. Firstly, I would like to thank you for your insights. Your work is really interesting. For my question, I would like to ask, for example, if we want to isolate the compound which has never been isolated before, which means it's not present in any library,
Yeah.
in any compound library, and we want to isolate a specific, let's say, biomarker out of a compound, out of a plant, sorry. And we have a general idea about the class of the compound. Let's say it may be phenol or flavonoid or any or from any class, but we do not yet know the compound specifically. So, can you give me the general
Yeah.
idea that how can we narrow down our compound, like from a class to the specific compound? Like, what can be the general flow chart for that?
Yeah. Yeah, this is the most difficult part of the natural product research. You isolate the new compound, and if you can find a new compound, it's very easy to get the publication. And yeah, one of the main purpose of the phytochemistry to find the new compound, yeah, the new skeleton, the new structure, and so. It depends. Yeah, it's very difficult to explain in some work, but in general, if you want to isolate the new compound, so the first one that you also use the traditional, the conventional extraction and isolation technique to first we must to isolate the compound. Yeah, you must to isolate this compound. You get the pure compound. And when you get the compound, you need to check that by TLC also that is the pure compound or not. And when we get the pure compound, we can also send out a sample for the spectrometric spectroscopic analysis. Yeah, we can also use on top the technique that we could analyze, for example, FTIR for the chemical function, the proton, carbon, and some for the new compound. I believe you need also the 2D, 2D NMR spectrometry, spectroscopy to analyze also. And if you get the more complicated ones, also you have the chiral center. It's more complicated, and you need also other technique. Yeah. And it's not easy. Yeah, it's not easy if you don't. Would you like if you want to isolate a new compound? But when you got a new compound, it's very interesting. You can got publication, and also the biological activity is also interesting. And for me, also for the semi-synthesize, it could also use this compound for the synthesize. Yeah. And yeah, I hope that I can show you a general idea about the isolation of new compound. Yeah. Normally, when we isolate when we work with natural sugar, and we also thinking about when if you lucky, yeah, you can get a lot of new compound, yeah, and if not, you also isolate the null compound. Another trends nowadays, normally they don't want to isolate the new compound, but they would like to study about the chemical composition of the compound. And you can also think about the SPLC MS, yeah, to study about metabolomic. That also give us the information about the chemical compound also. And normally in some cases it's enough for you to identify firstly to predict the chemical composition of the compound before for the biological activity test, and also for the phytochemistry study later. Yeah. Yeah, I hope that I can explain a little bit about the work for the isolate of new compound. Yeah, with you. Do you have other question?
Yes, thank you so much for your answer.
Okay, great. Any more questions? Okay, not yet. Well, actually, I have this one questions because you also doing this semi-synthesis projects, right? So, can you explain explain on what the rationale behind choosing what specific reactions that you want to use, or what kind of functional groups that you want to add that will give a specific potential in the applications for the therapy? Can you explain a little
Yeah.
bit on that?
Yeah, there are two. Yeah, normally, I got for example, I can isolate alpha-aminosin very easily, and based on the structure of alpha-aminosin, I show that they are the phenol group, they are the alkane group on the compound, and I start to think what kind of reaction that we can apply for this compound. So for the phenol group, there are lots of reaction that we can apply with the substitution reaction. And for the alkane group also, we can also hydrogenation, we can also cut the double bond, also do other kinds of possibility. There are another part that I don't want to put in this lecture because the time is only for 1 hour. I would like focus on the isolation and semi-synthesize. I have also in our group, there are one colleagues, they work on about the molecular docking. And so first we must to design the drug based on the molecular docking screening, in silico screening. So we draw on of the potential or possibility based on the chemical structure, and we screen around the 400 centon that we can. We hope that we'll have the bond activity. So in our group, we focus on the chemokine receptor, CXCR. So they are family CXCR 1, 2, 3, 4. And normally CXCR one of them we focus on now is the CXCR3. That's related to the bone disease, osteoporosis disease. So we're screening around 400 compound, and after that we identify also for the natural compound and for the semi-synthesis compound also, and that will guide us to choose which reaction, which functionality that we will semi-synthesize to get the chance to obtain the bioactive compound. Yeah. So
Okay, interesting. Thank you for the explanations. And then actually when you do those kind of reactions, you will get several compounds, right? And then how do you choose? I mean, you will also evaluate or do the bioactivity assay to all of the compounds that you.
yeah.
Mhm.
Yeah, I normally now I build a library. So I just quite a long time ago. And so I started this project around 4 years ago. And first we design, we isolate the natural compound, and now we focus on the semi-synthesized. And we have now around 50 to 20 natural compound and also semi-synthesis compound for the evaluation of the bond activity. Yeah.
Okay.
So
For the
yeah.
isolated compounds, do you do the isolation yourself, or you're just by, because there's a lot of common isolates that you can buy, right?
Yeah. We can also buy the alpha-aminosin from Sigma Andric, and also from I don't know if you know the Maclean from China. Yeah, Maclean,
Okay.
you can also buy it from commercial source. Yeah, you can also buy alpha-aminosin, but other Covanon, Cochinchinona, you cannot buy on the they are not commercial source. But we can isolate very easily the alpha-aminosin. Yeah, with a very high quantity, and it's not expensive also. We can collect this.
Okay.
Yeah.
Okay. Is there any more questions from the audience? I have one more question actually,
Yeah.
but let's wait from the audience first if they have any more questions. No. Okay. One more questions. It's interesting that you use Medaka rather than the zebrafish, given that zebrafish is more commonly used, right, worldwide. Is there any specific reason why you use Medaka?
Yeah. Yeah, this was done by my colleagues in Hanoi. So normally she also use Graphis also, Graphis also. But Medeka, for now she told me that's very convenient for study because it's smaller than Graphis, I believe. It's smaller and that we can also get the result very quickly. So that's why.
Okay.
And
Okay.
also because they have the model, they use the transgenic,
Oh,
to make
okay.
that's
So
we
they
have
have the transgenic.
model,
Okay.
this model for bond specific for bond activity. So
Mhm.
that's
Okay.
why we
Okay,
use that.
thank you very much, Dr. Tats, for the excellent presentations and also explanations. And also, I would like to thank the audience for your participations and very in a very engaging discussions. So next, as a gesture of appreciations, the committee would like to present an e-certificate for you, Dr. Tat. So we kindly ask our Vice Deans, Prof. Fadlina, to give the certificate of appreciations for Dr. Tak.
You.
Yeah. So, Dr. Tak, can you please stop sharing your PPT because it's still in the sharing mode. Okay, thank you very
Okay.
much.
Okay, thank you very much, Dr. Ta, for your very interesting presentation. Hopefully, the participants who are present here will gain new insight regarding natural product and isolation. I think our natural resources that can be developed into natural product are mostly similar, right? So maybe in the future we can collaborate in this related this product. Once again, thank you, Dr. Ta, for your presentation.
Thank you. Thank you. Okay.
Okay.
Thank you. And so it's now to say goodbye. Hope you, I hope that I can visit your faculty in the future because I saw that a very
Yeah.
modern facility for research. And also, I would like to invite you in the future if we have conference or some co-exchange to come to our university to visit.
Okay. Okay.
Also.
Okay. Nice. You are very welcome.
Thank you. Thank you. Hope to
Yeah.
see you
Yeah.
soon.
Yeah.
Could you
Nice
wait
to
for
meet
a while,
you.
Dr. Tak?
Yeah,
Sorry.
yeah,
So
yeah.
we will have a group photo after this. I
Ah,
Oh,
missed
yeah. Right.
okay.
for a bit. Okay.
Okay. Okay. Budona, here for your
Yes.
appreciation.
Prof. Fadlina.
Already as a moderator for this morning session. Thank you very much.
My pleasure. My pleasure. Thank you for the opportunity.
Yeah. Still mute, Donna.
Okay.
Okay.
Okay, now let's take a group photo for documentation. Kindly turn on your cameras, everyone, and smile for the photo. For the committee, please assist with the photo sessions.
Okay, everyone, I will take a picture in 3, 2, 1. Okay. Okay. For the next slide. Okay. 3, 2, 1. Okay, thank you.
Okay,
Okay.
thank you,
Thank
everyone.
you, Dr.
But
Ta.
before we
Yeah.
conclude, I would like to remind you to complete the attendance and also evaluation form if you haven't already. So this brings us to the end of our sessions today. Thank you all for your participation and also attention. I hope today's lecture will give you an insightful and also inspiring for your next endeavor. And I'm Donna Mareta Aryastanti signing off. See you in the next sessions of the third international virtual course. Assalamualaikum warahmatullahi wabarakatuh. Bye everyone. Have a great day.
Okay, Waalaikumsalam.
Thank
Thank
you.
you, Dr. Ta.
Bye-bye.
Yeah. Hello, Tony. I see you. Hello. How are you?